Hi everyone. Today I am going to discuss with one more property. After that, Cayley-Hamilton theorem and diagonalization of a square matrix, etc. So, in the closing time yesterday, 2 to 3 properties I told. Please continue that. One more property. This is asked only one time in 2005. If lambda is an eigenvalue of matrix A with corresponding eigenvector x, then the matrix A, I is the corresponding identity matrix, I, A. For example, A is a 2 by 2 matrix, I is also 2 by 2 matrix, has eigenvalues lambda plus 1, comma, lambda minus 1 and eigenvectors x, comma, x minus x respectively. So please by heart the yesterday last 3 and this property also. Statements asked. One time gate question asked this regarding on this property. That's why I put 2005. Now the next one is Cayley-Hamilton theorem. Every square matrix A satisfies its own characteristic equation. Easy to understand, easy to remember everyone, this result. So A satisfied its characteristic equation. Similarly, B matrix satisfied its characteristic equation. What is the application that is advantage used to find A inverse without adjoint and at A and to find higher powers of A square, A cube, A power 4. Sometimes all these which are expressed as lower polynomials of A. For example, A is a 2 by 2 matrix. Its higher powers A square, A cube, etc. which can be expressed as linear polynomial in A. If A is a 3 by 3 matrix, its A inverse and A square, A cube, A power 4, etc. are expressed as quadratic polynomial in A. Okay, that is. Application. Finding A inverse and higher powers of A, that is A square, A cube, A power 4, etc. And all these A inverse, A square, A cube, etc. expressed as lower polynomials in A. Lower means if it is a 2 by 2 matrix, first degree polynomial in A. If it is a 3 by 3 matrix, A square, A cube, A inverse, etc. expressed in quadratic polynomial in A. If A is a 4 by 4 matrix, A inverse, A square, A cube, A square is expressed as linear polynomial in A. Okay. A cube A power 4 also is expressed as linear polynomial in A if A is a 2 by 2 matrix. If A is a 3 by 3 matrix, then A inverse A cube, A power 4, etc. expressed as quadratic polynomial in A. Okay. Example 1. This question asked in 2013. The E values, that is eigenvalues, of a 3 by 3 matrix. Please remember, if A is a 2 by 2 matrix, A inverse, A square, A cube, etc. can be expressed as first degree polynomial in A, that is linear polynomial. If A is a 3 by 3 matrix, A inverse, A cube, A power 4, etc. expressed as quadratic polynomial in A. That is the meaning. Or 2 comma 2 comma minus 1, then 3 by 3 matrix A. A inverse is option A, 1 by 4, 3A minus A square. Option B, 1 by 2, A square minus 2A. C, minus 1 by 2, A square plus 2A. Option D, minus 1 by 4, A square plus 2. Here the matrix is not given but eigenvalues. That's why A inverse we cannot find directly the 9 elements of A inverse. In that case, this is another application. If suppose A is a 3 by 3 matrix, then we can find A inverse without finding adjoint A using this method also. Okay. Solution. Let lambda is equal to 2, 2 minus 1 be the eigenvalues of the matrix 3 by 3A. Then the characteristic equation is, so from the characteristic equation, after solving lambda equation, we get lambda values. Now it is given reverse, that is backtracking. So lambda value is given. How to find the corresponding equation? When you know roots of an equation, how do you find the corresponding polynomial? Product of the factors, respective factors. So what are the 3 factors for this equation? Lambda minus 2, lambda minus 2 and lambda plus 1. Product of these 3 will become lambda cube equation, that is characteristic equation. Lambda minus 2 into lambda minus 2 into lambda. This is just by basics method only, 8th, 9th class, polynomials, factors, roots, equation, that chapter. So you know how to multiply, first 2 and then with third, or this is, you can apply theory of equations from 11th class, direct multiplication also. Okay, lambda cube minus 3 lambda square plus 4. Okay, so just now Cayley-Hamilton theorem, when you have an equation like this, lambda is replaced by the matrix A, that is called satisfies. Every matrix A satisfies its characteristic equation, which implies A cube minus 3A square plus 4I. When a constant term is present in the characteristic equation, then only inverse exists. When a constant term is absent in the characteristic equation, then A inverse does not exist. This is from our BTech first year, first semester, Cayley-Hamilton theorem. Okay, so when a constant is there, when a constant term is there in the characteristic equation, the corresponding polynomial term is that number into I, that is 4, 4 into I, minus 3, then it becomes minus 3I, plus 2, it becomes plus 2I, is equal to null matrix. Okay, since by Cayley-Hamilton theorem. multiply both sides by A inverse. We get, that means each term multiplied by A inverse. A inverse into A cube, A square. Just using that, A power m into A power n is equal to A power m plus n. Like that. A inverse into A cube is A square. A square into A inverse is A. That is 3 into A. Next, 4 into A inverse into I is A inverse. So, identity matrix into any matrix will give any matrix only. So, plus 4 into A inverse. 0 into any matrix is 0 matrix. So, we need A inverse except A inverse in the left side. Remaining term shift into the right side and then dividing by 4 will gives A inverse is equal to 1 by 4. The two terms will shift to right side, becomes opposite symbols. 3A, that is symbols changed. 3A minus A square. So, which of these options? So, answer is option A. The next question asked in 2012. Given A is equal to minus 5, minus 3, 2, 0. And I is equal to identity matrix 1, 0, 0, 1. Comma. The value of A cube is option A. 19A minus 30I minus 19A plus 30I 19A plus 30I D minus 19A minus 30I. Solution. We can apply by normal method, not only Cayley theorem. A into A square, and then A cube. Then substitute the given A and identity matrix in each of the option. Whichever gives the value of A cube, that option is the answer. Okay. So let us see the beautiness of Cayley-Hamilton theorem. So first, characteristic equation, that is CHEQ, is determinant. Sorry. Subtract lambda from the diagonal elements. Minus 5 minus lambda minus 3. 2. 0 minus lambda means minus lambda equal to 0, which implies AD minus BC. 5 lambda plus lambda square plus 6 equal to 0, which implies lambda is replaced by matrix A, that is Cayley-Hamilton theorem. A square plus 5 lambda becomes 5A. 6 number 6 becomes 6 into I. 0 becomes 0 matrix. Since by Cayley-Hamilton theorem, capital C dash capital H stands for my short form of Cayley-Hamilton. Okay. They are asking A cube. So shift to other two terms except A square to the right side. Minus 5A minus 6I. Let us say equation 1. Now implies multiply both sides by A. A cube is equal to minus 5A square minus 6A. When we want A inverse, what I have done in the previous problem, multiply both sides by A inverse. When we want A cube, already we have A square. So just multiply both sides by A. So here 5A square is not in the options. So we should eliminate this A square by the help of equation 2. So minus 5 into equation 1, minus 5 minus 6I minus 6A. So now simplifies to minus 5 into minus 5A is 25A. 25A minus 6A is 19A. Minus 5 into minus 6i is 30i. That is plus 30i. So answer is option C. You can verify by ordinary method also. That is find a square a into a. Then a square into a gives a cube. Put aside your a cube value. Substitute a and I in each option. Whichever option answer is same as a cube matrix, that option is the answer. Now, see, many of you not understanding, for example, what is satisfying the equation. This is your a. What is a square? A into a. That is minus 5 minus 3 2 0 into minus 5 minus 3 2 0. So 25 minus 6 19 15 and this is minus 10 and this is minus 6. So now this is called, how do you get this is? By Cayley-Hamilton theorem. Just substitute by lambda. Okay, so consider a square plus 5a plus 6i. So I am simplifying this. I have to get zero matrix. That is called satisfying this equation. This is characteristic equation. Okay, so a square value 19, 15, minus 10, minus 6. 5 into a, that means every element of the matrix A multiplied by 5. 5 into minus 5, minus 25, 5 into minus 3, minus 15, 5 into 2, 10, 5 into 0, 0. Plus 6i, 6 into these 4 elements, 6, 0, 0, 6. Sum of the 3 matrices means corresponding elements to be added. So 19 minus 25, that is minus 6 plus 6 gives 0. 15 minus 15 cancel, 0 plus 0, 0. Minus 10 plus 10 cancel, plus 0 gives 0. Minus 6 plus 0 plus 6, 0. This is called, finally we got right side of this. That is called Cayley-Hamilton theorem. That means, in the characteristic equation, if you put lambda is equal to the given matrix A, definitely that left hand side value, a square plus 3a, whatever it may be, it becomes 0. Okay, that is, this is your characteristic equation. Substitute lambda. That is a square plus 5a plus 6i. Simplify. Definitely you will get is equal to 0. That is, when x value is satisfying an equation, that x is called root of the equation or not. Similarly here also. Now the next one is diagonalization. Of a square matrix. A square matrix A n cross n is said to be diagonalizable if P inverse into A into P is equal to D, or A is equal to P into D into P inverse. We know A only. What about other P and D? Here I am writing where D is equal to diagonal matrix, that is diagonal, writing by diagonal elements only, lambda 1, lambda 2, so on, lambda n. And P is equal to a matrix whose columns are linearly independent eigenvectors of the matrix A, that is x1, x2, so on, xn. Here, lambda 1, lambda 2, so on, lambda n are the eigenvalues of matrix A and x1, x2, so on xn are n linearly independent, Li stands for linearly independent, eigenvectors of matrix A. Also, if they ask the question P inverse into A power n into P, just the power n is affected on the middle term as well as on the right side. P and P inverse, no change. So, they provide some square matrix, whether it is diagonalizable or not. Then your first step is find eigenvalues of the given matrix A. Let them denote lambda 1, lambda 2, etc. For each eigenvalue, you find the corresponding eigenvector x1, x2, so on, and compulsory x1, x2, so on, xn. That is, all eigenvectors are linearly independent. Yesterday I told you. How do you prove some vectors linearly independent? That means determinant not equal to 0. Okay. Then consider all these n linearly independent vectors as columns in a matrix. That matrix is here P matrix. Once you know P matrix, how do you find P inverse? That is adjoint P by det P. Once you found that P inverse, then P inverse into A and then multiplied P, product of these three matrix is equal to compulsory diagonal matrix. Otherwise it is your mistake. Okay, that D is called diagonal matrix. Diagonal matrix, you know the meaning. Non-diagonal elements 0. What are diagonal elements in this D? Compulsory eigenvalues of the matrix A. Okay. Now in this a note point. If det P is equal to 0 or the number of linearly independent E vectors of matrix A is less than n, n is the order of the matrix, then A cannot be diagonalizable. Take care of this. Yesterday, 2007, that problem 2102, find the eigenvalues, eigenvectors of the matrix. There we got lambda is equal to 2, 2 repeated eigenvalues. But how many linearly independent eigenvectors? Only one linearly independent vectors. So for the matrix A 2101, we got 2 eigenvalues, but number of linearly independent eigenvectors is 1. For that 2 by 2 matrix, what is the order of the matrix? N is equal to 2. So number of linearly independent vectors less than order of the matrix in that problem. Hence that matrix yesterday cannot be diagonalizable. That means we cannot make into this matrix T. See example. This question asked in 2006. It is a diagonalization related method or normal method also you can apply. Let lambda 1 is equal to minus 1, lambda 2 is equal to 3 be the eigenvalues and kindly excuse me. Please strike this. For a given 2 cross 2 matrix A, it is observed that A into 1 minus 1 is equal to minus of 1 minus 1 and A into 1 minus 2 is equal to minus 2 into 1 minus 2. Then matrix A is option A is equal to 2 1 minus 1 1 minus 1 0 0 minus 2 into 1 1 minus 1 minus 2. Option B. A is equal to 1 1 minus 1 minus 2 into 1 0 0 2 into 2 1 minus 1 minus 1. Option C. A is equal to 1 1 minus 1 minus 2 into minus 1 0 0 minus 2 into 2 1 minus 1 minus 1. Option D. A is equal to 0 minus 2 1 minus 3. So depending on the options, majority of the options is product of three matrices. In the above definition we have product of the three matrices. So that's why I am giving priority to apply diagonalization for this solution. So now what is given? A into 1 minus 1 is equal to, minus can be written as minus 1 into 1 minus 1, and A into 1 minus 2 is given as minus 2 into 1 minus 2. It looks like eigenvector x eigenvalue lambda matrix definition. If I denote this bracket x1 1 minus 1, the right side is also denoted by x1, so that minus 1 I can denote lambda 1. So Ax is equal to lambda x or not. Similarly, for a 2 by 2 matrix you have two eigenvalues and the two eigenvectors in this. If I denote 1 minus 2 by the vector x2, on the right side the same vector x2, the pre-multiplication I can denote a number lambda 2. Okay, so it looks like Ax equal to lambda x, both equations, correct or not? So implies, okay, your D matrix, diagonal matrix lambda 1 with diagonal elements as eigenvalues 0 lambda 2, just by comparing that notation. So minus 1 0 0 minus 2. Capital P matrix, matrix forming whose columns are linearly independent eigenvectors. There are two eigenvectors x1 x2. So I don't know whether they are linearly independent or not. If they are not linearly independent, automatically they are linearly dependent. When the vectors are linearly dependent, automatically yesterday the short form procedure I told you, determinant 0. When the determinant 0, the matrix cannot be diagonalizable. Let us see determinant P equal to 0 or not equal to 0. So x1 eigenvector is 1 minus 2 and x2 is, x1 is 1 minus 1, x2 is 1 minus 2. Implies det P, 2 by 2 matrix det AD minus BC, minus 2 plus 1, that means minus 1 not equal to 0. So success, that means P inverse exists. Okay. So what is P inverse? The first day of matrices I told you, 2 by 2 matrix, adjoint P by det P. So adjoint P 2 by 2 matrix 10th class formula given. Okay. So 1 by det M is 1 by minus 1 into adjoint of this matrix P minus 2, interchange diagonal elements, non-diagonal elements multiplied by minus. So this minus multiplied by each and every element, 2 1 minus 1 minus 1. This is P inverse. Now they are asking the matrix A. Okay. So according to the diagonalization, the matrix A can be written as product of three matrices, P into D, P inverse. We got P inverse and P D. Therefore, A is equal to P into D into P inverse. What is P? So when det P not equal 0, so here that is you can say that x1 comma x2 are linearly independent E vectors of matrix A. Okay. What is P matrix? 1, 1, minus 1, minus 2. What is D matrix? Minus 1, 0, 0, minus 2. What is P inverse? 2, 1, minus 1, minus 1. Any option? So, answer is option C. So, by that time, if you do not recollect, this is this example related to diagonalization, then I will tell you alternate method also. Don't worry. Here, using diagonalization. Without eigenvalues method also I am doing. Method 2. So they are asking 2 by 2 matrix, A 2 cross 2. 4 elements, let us take A, B, C, D. Okay. Given A into 1 minus 1 is equal to minus of 1 minus 1 and A into 1 minus 2 is equal to minus 2 into 1 minus 2. Just substitute the given matrix A. This 2 by 2 matrix multiplied with column. So, first row into column A minus B. Second row into this column C minus D is equal to minus multiplied by every element of column. So, simplifies minus 1, 1. And similarly, substitute A here. So, first row multiplied by 1 minus 2 will give A minus 2B. Second row CD multiplied by 1 minus 2. So, C minus 2D, which is equal to every element of here multiplied by minus 2. Minus 2 plus 4. So, both are column matrices, left and right side. When two matrices are equal, corresponding elements to be equated. So, this simplifies to A minus B is equal to minus 1. C minus D is equal to 1. On the other hand, A minus 2B is equal to minus 2. C minus 2D is equal to 4. Solving AB equations will give AB values. Solving CD equations, we get A is equal to 0, B is equal to 1, C is equal to minus 2, D is equal to minus 3. Just by subtracting like that. So, 0 minus 1 is equal to minus 1, 0 minus 2 is equal to minus 2. Minus 2 plus 3 becomes 1, minus 2 plus 6 is equal to 4. Okay. So, therefore, A is equal to 0, 1, minus 2, minus 3. But this value is not in the options. Correct or not? So, in each option, multiply. In ABC options, it is product of three matrices. Just multiply. That matrix value is same as this matrix. That option is the answer. Okay. Now, in option C, so you can have a doubt. Why you are starting with option C? Because I know the answer by method 1. That's why I gone through directly option C. Or you can find product of these three matrices. That value of that matrix, finally that matrix obtained is same as this. That option is the answer. Okay. So in option C, A is equal to how much given? 1, 1, minus 1, minus 2 into minus 1, 0, 0, minus into 2, 1, minus 1, minus 1. So first I am multiplying these two. Matrix multiplication into first row into first column minus 1, first row into second column minus 2, second row into first column plus 1, second row into second column 4 into this matrix 2, 1, minus 1, minus 1. So first row into first column minus 2 plus 2 cancelled 0, minus 1 plus 2 1. Second row into first column, 1 into 2 plus 4 into minus 1, minus 2. Second row into second column, 1 into 1 plus 4 into minus 3. So, this is we got. In all other options, already option D is not satisfying our A. Similarly, you can cross check by A, B, normal multiplication of 3 matrices will not give this 0, 1, minus 2, minus 3. Okay? Note. The dimension of the null space of matrix A m cross n is denoted by eta of A. Dimension of the range space is denoted by rank of the matrix A. Rank of the matrix A symbol is row symbol. Eta is also a Greek letter which stands for dimension of the null space. Dimension of the range space is also called rank of a matrix A and given by only one time asked in long back 90s, 1990 and then 2013. Okay, instrumentation question this one asked, which is useful in actually vector spaces and in some where technical subjects also. This point, rare case. Okay. Eta of A is equal to number of columns in A minus rank of A. You know how to find rank of the matrix and how to identify number of columns. The difference is called dimension of the null space of a matrix A, which is also called in science students, they are also called this point nullity of a matrix A, which is a word in vector spaces, science subject vector spaces. Okay. Example C. 2013. The dimension of the null space of the matrix A is equal to 3 by 3 matrix 0 1 1 1 minus 1 0 minus 1 0 minus 1 is A 0, B 1, C 2, D 3. just this definition related to rank of a matrix only. Where I underlined by blue color row of A, this is rank of A. So number of columns is 3. Now find the rank of the matrix. A is equal to 0, 1, 1, 1, minus 1, 0, minus 1, 0, minus 1. So here the first diagonal element is 0. We should interchange these two because below the diagonal element, if any non-zero element, immediately interchange the row operation. Otherwise, you will be in trouble. Don't take this is a first non-zero element. Okay. So this is already done in 2 days back, this rank of matrix. So R1 interchanges R2 equivalent to 1, minus 1, 0, 0, 1, 1, minus 1, 0, minus 1. So I hope that everyone following and understanding. Okay. So when a diagonal element is 0, again second time I am telling, look at its exact down elements. If anything non-zero, then bring that non-zero element into the diagonal 0 element. So that is the best method only. Otherwise, if you go to the next element, considering as first non-zero element, you will be in trouble in the next steps by getting rank of matrix. Okay. So now this is the first non-zero element. Already R2 element 0. We should apply R3 row operation with R1 by making R3 element 0. R3 plus R2 equivalent to R3 only changes. 1, minus 1, 0, 0, 1, 1, minus 1 plus 1, 0, 0, minus 1, minus 1, minus 1 plus 0, minus 1. Now, the first non-zero element in the second row is plus 1. We have to make its down element minus 1, 0. This is R3 and this is R2. So, apply a R3 operation with R2. That is R3 plus R2 equivalent to only R3 changes. Sorry. R1, R2 remains same. 1, minus 1, 0, 0, 1, 1, 0 plus 0, minus 1 plus 1, 0, minus 1 plus 1, 0. So, below the diagonal, 0 is row echelon form. The number of non-zero rows is 2. Therefore, rank of A is equal to 2. Okay, comma. Number of columns in A is 3. Therefore, eta of A, that is dimension of the null space of the matrix A, is 3 minus 2 is equal to 1. So 1 is the answer. And there is a last point. It's a rare case like this dimension, LU decomposition method, that is factorization method, triangularization method, which is a descriptive question in BTech also. That is electrical one time asked, EC one time asked, CS one time asked, but in 2016 that was mentioned separately in EE stream, that is electrical engineering stream only. Okay. LU decomposition method, which will take 5 to 10 minutes only, hardly, or Kraut's triangularization method. Okay. This is another method to solve system of linear equations non-homogeneous. 2 equations in 2 variables, 3 equations in 3 variables, more than, that is 4 equations in 4 variables, that is become laborious. Okay, this is especially useful for 3 equations in 3 variables and 2 equations in 2 variables. What exactly? Once you write the given equations in matrix form, that is Ax is equal to B, where A is the coefficient matrix. So factorize the matrix A into 2 simpler matrices L and U. That is, factorization means product of the 2 matrices. So express the matrix A is equal to L into U. That is product of L and U. What is L? What is U? L is lower triangular matrix. U is upper triangular matrix. Okay? Without row operations, column operations. So I am explaining the method. Consider Ax is equal to B, equation 1, comma, a system of 3 linear equations in 3 unknowns, that is variables, x, y, z, or x1, x2, x3, whatever you like. Okay? Or x1, x2, x3. That is, I am considering just 3 linear equations in 3 unknowns. Understood? Now, next step, let A is equal to L into U, equation 2, where L is equal to a lower triangular matrix, considering the elements, 9 elements as L11, 0, 0, L21, L22, 0, L31, L32, L33. What is lower triangular matrix? Elements above the diagonal 0. Remaining 6 elements are L elements. That's why I put the symbol small l. Matrix is denoted by capital letters. Its elements are denoted by small letters. Is a lower triangular matrix. And U is equal to U11, U12, U13, 0, U22, U23, 0, 0, U33 is upper triangular matrix. So for convenience, take either diagonal elements of L is equal to 1 or diagonal elements of U is equal to 1. Then only we can solve that method. Because A is a 3 by 3 matrix containing 9 elements. But U containing 6 unknown elements, L containing 6 unknown elements. Total number of unknown elements 12. How it matches? Left side is A matrix. A matrix we don't know elements. Let us take A11, A12, A13, that is 9 unknowns. But here total 12 unknowns. So that's why either these 3 diagonal elements 1 or these 3 diagonal elements 1. So that is the procedure. For convenience, take L11 is equal to L22 is equal to L33 is equal to 1. That is the diagonal elements of 1. Then equation 1 becomes. So what are these? Diagonal elements of L matrix. Okay. So substitute A is equal to LU in equation 1 becomes L into U into X is equal to B. According to associative property, I can write L into Ux is equal to B. Okay, let us say equation 3, since associative property. Matrix multiplication is associative. Okay, now I am taking writing ux is equal to y. U is now known after solving this. X is xyz. So this is unknown. So when X is a column matrix, U is a 3 by 3 matrix. Multiplying this, you will get another column matrix that is denoted by Y. So what is that Y? Where Y is equal to column matrix Y1, Y2, Y3. Okay. So then equation, let us say this is equation 4. Then equation 3 becomes, what is equation 3? This is Ux is equal to Y. Substitute here. L into Y is equal to B. So this is a directly say 5 equation. L is known, right side B is already given, Y is just lower triangular matrix which is obtained by the elements Y1, Y2, Y3 by forward substitution. Okay, solve equation 5, comma, which gives Y1, Y2. There is nothing explanation, each and every point I am writing. Values. Now after getting Y1, Y2, Y3, now go to that, Ux is equal to Y. Here Y solved, now X is unknown, U is already solved from 4. Okay. Now solve 4, which gives X, Y, Z values. Okay. So nothing explanation, just observe. Have a break.